So the last section of this we're going to look at is the actual process itself. And I've talked through these a bit as we've gone, but I just want to give you a full process summary. Most of you have started doing this already in lab, but just to kind of review it. So aerosol penetrants type 1 and type 2, when they're in aerosol form, we want to spray to cover either the entire part or the entire area of interest. We don't always have to spray the entire part if there's a known area where. When we did like the combustion or the turbine case inspections I talked about, we didn't spray the whole case. There was a critical area that we had to inspect, and that's where we did it. The only time they did the entire case was during an overhaul when the case was removed from the engine. But for on-wing inspections, we just did the 3 o'clock and 9 o'clock positions because that's where the cracks would occur. Something with the vibration and the way it was mounted and everything else, it would cause that work hardening to occur there, and that's where they would crack in service most of the time. We allow it to dwell. We allow the penetrant to sit on the part for 10 to 30 minutes. What's happening during that dwell time? What is our penetrant doing? Capillary action is going to pull it into any kind of cracks, discontinuities, or other features that we're trying to find. And then we need to remove our excess penetrant. We're going to start with a dry cloth. So just a clean, dry, essentially those white wipes, white paper towels. And once we've removed the majority, we want to wipe, carefully one direction. You don't want to blot because, right, the developer will do that same thing. We don't want to blot the stuff back out of those cracks and discontinuities. So we're going to kind of wipe over one direction. You can go a second direction, maybe flip your cloth over or turn it right side out so you have a clean surface each time you're doing it. Then we're going to take a new clean cloth, damp it with cleaner, and we're going to do a final wipe or two gently to remove residue on the surface. Between the penetrant dwell stage and before we put on developer, we do not want to spray our part with the cleaner. Do not spray the cleaner directly on the part. Because what will happen is that cleaner will then sit on the surface and capillary action will pull it down into the cracks, and it will have the potential to dissolve the penetrant back out of the cracks that we are trying to find. So that's why we spray it on a damp rag, or we use it to make a damp rag rather than spraying it right on the surface. It'll cause you'll over clean the part is the term for it. After we've cleaned the part, aerosol penetrants, I thought I had liquid penetrants. Anyways, liquid penetrants, we do basically the same thing when we're applying it. Just this. Actually, I go through the process. That's why. Sorry, I got ahead of myself. Applying the developer, we have dry powder, carrier, and this can be used with an aerosol penetrant. It can be used with a liquid penetrant. It can be used with types. You can kind of mix it up, but most of the time, if you're using an aerosol-based penetrant, you're probably using an aerosol-based developer because you're doing a portable type function out on the line, out in the field, versus a bench where dry powder is more commonly used. Just know though, with the dry powder developer, it's a carrier. It doesn't actually leave a contrast surface on there like the aerosol does. So when we use the aerosol, the non-aqueous solvent in aerosol cans, we're going to use a thin, even coat. That is going to leave a chalky, when it dries, it'll leave a chalky residue on the surface. Whereas the dry powder that we use does not. The dry powder, it has a coating of developer on each one of those little particles, and that coating sticks to the areas where the penetrant still has caused some moisture, where there's still a little bit of moisture from the penetrant and cracks now. That's why it's important to dry the part before we apply a dry powder. The non-aqueous solvent, that's going to leave a thin layer. We don't want to overdo it. We also don't want to, we want to make sure we spray it evenly and smoothly, always starting and stopping, pushing the spray nozzle off to the side of the part so that you don't get one of those kind of circle drip spots that you get if you do that you're familiar with from painting. And same thing also, just like paint, where if you over apply it and it drips, if you over apply developer, and it can drip before it has time to dry and leave that coating. The water soluble, water suspendable, the test piece does not have to be dry before we apply it. So if you're using dry powder, if you're using non-aqueous solvent, typically you're not using non-aqueous solvent with a water wash, but with dry powder, you definitely want to make sure your part is dry. Otherwise, those powder particles that aren't supposed to stick to the part they'll cake on it, and they'll give you a false indication. So we have to make sure it's dry. So that's one of the advantages with water soluble, water suspendable, is that because they're already in water and it's the medium to transfer it on there, we don't have to spend that time drying the part. Okay. The drying occurs after the developer is applied. You put it in the oven to dry. It also serves as the developing time. Where as it's drying, it's also developing. It's also pulling that. It's also blotting that developer back out into the developer surface. So it can be a little bit faster. With that, then we need to do our inspection of our part before. We always want to make sure we have a detailed visual inspection. If we find something in a detailed visual inspection that makes the part unserviceable, there's no point in continuing on and doing the rest of the NDT inspection. So, aided by your magnifying glass, flashlight, blacklight, or visible, depending on what kind of penetrant, you can actually sometimes even use a blacklight for initial inspection. Sometimes you can pick up some weird stuff with a blacklight. Occasionally, surface changes will reflect blacklight differently. So you'll sometimes see that. Mirrors, borescope. There are actually blacklight borescopes where you can do a fluorescent or mag particle inspection, and then if you need to look at internal areas, you can stick a borescope in there that has a black light on the tip instead of a standard white light. And then ultimately your black light for type 1 inspections and your visible light for type 2. Okay. So just to review, we talked about black lights with mag particle, but ultraviolet light is the 2,000 to 4,000 angstrom or 200 to 400 nanometer wavelength. Black light specifically is the 3,500 to 3,800 angstrom or 350 to 380 nanometer wavelength. And the reason, well, anyone remember, why do we use that versus ultraviolet light? Penetrance, fluorescent penetrance will glow under basically any type of ultraviolet light. Why do we use black light rather than just ultraviolet light in general? What's the reason for that? Why do we spend all this money for these very special filters that narrow it down to a very narrow band? Why not just use a standard, just an ultraviolet bulb? Anyone know where else we use pure ultraviolet or strong ultraviolet? Tanning beds, right? What else? Ultraviolet's used in sterilization. It kills things, right? What's that? It helps plants grow too, greenhouses. But the big thing with ultraviolet is it's hazardous if you get too far away from that visible spectrum. Okay, as you go from, the visible spectrum starts at that 4,000 or 400 nanometer. As you get those smaller waves below that 350 to 380 nanometer range, so you get into the 300 nanometer range, 250, 200 nanometer range, that's getting into the type of ultraviolet light that can be hazardous. It can cause skin burn, sunburn. It can cause eye retina damage and that kind of thing. It can actually lead to, with burns and that kind of thing, those are raise your risk of cancer. And so that's why we want to use these rather than a pure ultraviolet light, because of that. So we also have to be aware of our light strength, and we use a radiometer to test it of 1,000 microwatts per centimeter squared at 15 inches. So you hold your light 15 inches away. Your radiometer basically has a 1 centimeter squared element or test element, and it just makes sure it gets enough microwatts hitting that square centimeter worth of sensor and verifies your light's good. Now that radiometer has to be calibrated on an annual basis in order to make sure that when you're testing your lights, it's correct. The other thing a lot of radiometers will do is they'll have a black light sensor and a white light sensor. And so if you're doing a black light inspection, you can also make sure that you don't have too much white light in the vicinity if there's some question about it. If you're able to like tent yourself with a plastic bag or go into a dark room, it's usually not too big of a concern. But if there's some kind of a question that comes up, they can test it. So light, some of the lights we have, 100-watt mercury vapor bulb with a purple filter. We have 2 of those. They're going away though. They don't even make a lot of these bulbs anymore. If they are, you're finding ones that are old stock that have just been sitting around for a long time, but there's really no reason to make them that much. So industry is moving to LED light sources. So when our mercury vapor bulbs burn out in the lab, I'm not going to bother replacing them. It's not worth the cost to have them. So last part is to verify the process. You're doing this. Some of you have done this already. Others will do it when you do the lab. But we have what's called the TAM panel. I've shown it. I've held it up and showed it to you, and I did the demo for aerosol liquid penetrant inspection. But the panel used to check your penetrant quality, your process quality. So here, if you were looking at this, what level penetrant would you say they're using? Level 1? It's type 1, okay. What level? What's that? Level 3, probably. Okay, here's your half. 1, 2, 3, but you can't see the dot for level 4. Okay, it might be a level 2 and they just did a really good job with it. As you saw, you've probably seen, some of you have, you've been able to get this level 3 indication to start to just show up a little bit, but not consistently enough that you can inspect at a level 3 flaw size. What does this top part show right here? The top, so we got a top part that's glowing, a bottom part besides the flaws, the simulated flaws, is not glowing. What's that telling you? What's that? Coverage. Your coverage or how well you cleaned it. So here, there's not, what happens if you have a bunch of excess penetrant on this area down here that would be polished? What does that mean? You didn't clean it well enough. You underwashed the part. What happens if this rough surface on the top doesn't have any penetrant left on it? Tells you overwashed it, you overcleaned it, and likely reduced your ability to find cracks by washing out penetrant from some of the cracks. Okay, so it gives you an idea of if your process is good or not, and as well as your chemical. If your process is dependent on your chemicals working. Okay, the chemicals are going to have your developers, your penetrants, even the cleaners to some extent are going to have a shelf life, and if they're expired, they may not work as well as they're supposed to. But has anyone noticed anything about a bunch of the ones we have in the lab? A bunch of them are expired. We got a lot of them when I can't remember where. They got them from somewhere. They had a big batch of expired ones and asked if we wanted them. You can see, are they still working? They still work, but you couldn't use them on an airplane where you say that it's going to be, it can't be expired. Okay. So that wraps up liquid penetrant.